Before we start, let's do a quick audience poll just to wake up a little bit. Among you, who consider yourselves technical? Great. Thank you. Okay, so I see about 10 hands. All right. What about non-technical for any definition? Okay, great. About 20 hands. Who is not caffeinated yet? Okay, another 5 hands. All right, so we have something on the order of 10 technical, 20 non-technical, maybe 10 non-caffeinated, and missing data. Everyone else. Great. Okay, so I think I planned the talk for the right audience then. All right, so financial disclosures. I am an employee of Google, and I own Alphabet stock. And speeding right past that before I get any questions on that, our research here in the team, I come to you from a team at Google. We work on healthcare research. And we do work in a lot of different areas. Margaret kindly gave a great intro to some of the work that we're doing. And I will not talk about all of the work today. I'll focus on just one as an example. But we do have a lot of stuff that we've done out there. If you are interested, go to that URL that is hopefully visible right here. If not, it is goo.gle/health-scholar. So that's a short URL. Doesn't look like it, but it's a short URL. I promise you it goes to a Google Scholar page, not something weird. All right. So why are we here today? Why is everyone here mostly non-caffeinated and attending a pre-conference workshop early in the morning? We're here because there's been a lot of work in deep learning in healthcare. Just over the last 10 years or so, it has increased 100-fold. So that is not an error, it's actually 100-fold. And if you noticed, for those who are caffeinated, you might have noticed I used the word deep learning, not machine learning. And why is that? Well, let's take a look at the terminology here. What is AI? AI is artificial intelligence. It is a little bit of a nebulously defined term, but it refers to how to build tools to do tasks that traditionally you would think of as requiring intelligence. The definition of what that means has changed a little bit over time. Previously, you would consider things like optical character recognition, recognizing dates, numbers, letters on checks to be something that requires intelligence. Nowadays, we have a much more demanding definition of AI. Now, the smaller green circle in there, that's machine learning. Machine learning refers to the fact that instead of trying to explicitly program the algorithm to do something, we use data to teach the model what it is that we want it to do. So we have labeled examples that tell it to do this when you see this. Deep learning is an even smaller circle within that refers to techniques, a class of techniques that uses what we call artificial neural networks and many layers of computation to get to the final machine learning results. For the purposes of what we're talking about today and probably going forward for quite a while, machine learning and deep learning have a lot of overlap. And so for the most practical use cases, you can consider them mostly synonymous. So how do we train machine learning models? I alluded to it earlier. Let me see if this cursor appears. It does. Oh, there we go. OK. So hopefully that's partially visible. So the way we train machine learning models is by using labeled data. So in this case, for example, we have a labeled example of a cat and a dog. And these dots over here, they represent artificial neurons arranged in multiple layers. So what's happening in these neural networks is that you have the pixel values in these images going into these neurons. Each of the neurons perform a very simple computation. Usually all they're doing is weighting different pixel values differently. They pass on what it is that they output to the next layer, and so forth. Now, by having many layers of this computation, what then happens is that the model then outputs something at the very end. Usually it's just a single value. Now, what's interesting is that when you initially start this, you initialize this network usually from random weights. When you do that, the guess that's at the end has no meaning whatsoever. You can take the guess that's at the end and then apply a function that says, is it more likely to be cat or dog? So it just goes from 0 to 1. 1 is cat, let's say, and 0 is dog. Now, when you do that, the initial guesses are random. They have no meaning whatsoever. However, what you can do, interestingly enough, is to say, well, you got it wrong this time. How do you change the parameters of this network? You just go layer by layer in reverse order. You change it slowly, and then you go all the way back to the image. And after you've done what's called that reverse pass, you have now edited the weights in this network by a little bit. Now you do this for many more examples, again and again, for millions of examples and millions of steps. At the end of it, what you have is this network that has now adapted using data to then produce some kind of output, such that if you provide a new example of a cat or a dog, that final output that it produces now corresponds to the right answer, a cat or a dog. So at the core, this is what's happening in machine learning. The mathematical details here are a little bit more complex, but really what's most important here, the main concept here, is that there's an input that is some kind of complex data usually, and there's output, which is your desired behavior from the network. Everything in between, that's just math. You can work with folks to figure that out, but really it's about what is the input, what is the output. So why do we apply machine learning to medicine, and when is it most appropriate? It's most appropriate when you have data on which to train. You need the data to teach the model what it is that you want it to do. It is most appropriate when you have a situation where after you have the model that is capable of doing what you want it to do, you can then integrate the model somewhere, and it is a location where that expertise is needed, meaning you don't have enough humans or other tools available to do the same task. If there was free labor to do the same task, it may not be as useful sometimes to have these models. And lastly, it's most useful when the predictions that you create are actionable. You can do something different based on knowing the result of their prediction than if you didn't know the result of the prediction. Now, in terms of the running example that I will be using, this is about diabetic retinopathy or diabetic eye disease. And it's interesting because in the course of screening for diabetic retinopathy, a lot of places use fundus cameras. You sit the patient down, there's a chin rest, take a photo of the back of the eye, and you get that photo, send it off to a grader or ophthalmologist to do the grading, and based on what you see in the images, you can determine whether they need a referral to ophthalmology clinic or not. There's limited expertise to grade these images in some areas of the world, and that's where this can do a lot of good. So, what is AI and how do we apply it? Well, mentally, I will map it into 3 broad steps. First step is technical modeling. That's what a lot of folks would think of when you think of machine learning. That's all the math that's going on behind the scenes. That's labeling the data, that's evaluating the model. The middle step, the second step, is about what is the interface between the technology you're developing and people. People in the clinic, people in real workflows. And lastly, what is the system perspective? How do you make this work overall, such that at a system level, this is something that is self-sustaining that people want to use and continue to use? Most of my talk will be about the first step over here, the technical modeling. I'll touch very briefly on the other 2 steps, but the speakers coming right after me have great talks about those topics as well. So, what is technical modeling? This is a cheat sheet. When I was in college, I loved these things. Prepare a cheat sheet, and if it's an open book exam, you have that cheat sheet, you can refer to it. If you're going to take a photo or take notes, on my next slide will be a fully fleshed out version that has something on the right side. Now, what is on this cheat sheet? Well, unfortunately for you, this cheat sheet does not have the answers. It has questions. And the questions are the stuff that you should be able to answer if you're not technical. So the 20 of you who are not technical, you should be able to answer this. So the first thing on the cheat sheet is, what is the problem? Meaning, who is the patient population you're trying to serve? Why are you taking these photos or developing the model? What is the purpose here? Under what setting? Is this in primary care? Is this somewhere else? And why? Like, what is the actionable result from this? A cursory answer of these questions is pretty simple. It's a one-liner. But to get going more in depth, when you talk to a collaborator, you need to really understand this problem really well. Don't come to them with, hey, I want to do AI. No. I want to do AI for purpose X. What is that X over here? The second thing is, what should the model do? And what I mean by the model here is actually a little bit different than the actual machine learning. The actual machine learning model. What I mean here is, if you develop a tool based on this model, what should the tool accomplish? What do I provide the tool as input? What should it be outputting? How do I know when the output is correct? What is the ground truth here? And what is the performance target? Are you aiming for sensitivity, specificity? Do you need high sensitivity, or do you want high specificity in this case? What kind of data do you have available? How much of it is there? How much of it is labeled? How much of it is not labeled? That can come in useful as well. And any other constraints that you have. Should it be fast, cheap, good, all of the above, something else? Figure that out when you start a conversation here. All right, so that's the non-technical pieces. Now, when you meet with someone technical, they'll take the answers that you provided over there it'll start to try and figure out what the technical pieces of these are. Second part of the cheat sheet over here. Again, more questions. This time for the 10 technical people in the audience, right? So the modeling setup. How do you collect the data for the modeling? How do you split up the data to do modeling? How do you label the data? Do you need to get more labels? Or is it already available somewhere? You can just collect it. In terms of the actual model, what is it doing? Is it classifying the data? Category A versus B, cat versus dog, diabetic eye disease versus not. Is it doing regression? Is it predicting some kind of continuous value? What is the A1C value, for example? Is it a generative model, meaning not just the input is complex, but the output is also complex? Is it all of the above? Do you do all of the above so that the model learns more, a richer representation? And what architecture do you use? I'll give examples of these later. Pre-training, what does that mean? Well, this refers to a step before you actually train a model, where you prepare the model such that it can extract more useful features from the original complex input. I'll talk about why soon. Model training and tuning. This is where what we think is happening most of the time in machine learning. In reality, what's happening is that the machine learning person is kicking off a training run, going to sleep, and then checking on it after they wake up. That's that step over here. Model evaluation. How do you do the evaluation? Usually we call this a test set. Depending on your background and where you what papers you read, you will also see things called out-of-sample validation, external validation, or even clinical validation in regulatory settings. How do you do subgroup analysis? Why do you do it? To check for bias. What do you do in terms of sensitivity analysis? To check any assumptions that you have. What if you change the reference standard or the ground truth? And finally, assuming all this works and you launch it, how do you monitor for anything that's not going well? And how do you update the model over time? All right, so that's the cheat sheet. This is information overload. I recognize that. We'll go into an example shortly. All right, the example is for diabetic eye disease. The input is a fundus photo, so RGB pixel values, a few hundred wide by a few hundred tall. And the output that we want to get is a 5-class diabetic retinopathy scoring, so ranging from none to proliferative. And the purpose of doing this is to do DR screening for referral to ophthalmology clinics. And the place that you do the screening might be in primary care or might be in other clinics, diabetic clinics, for example. The data that was available was about 100,000 images, and we could do human labeling to get the right ground truth for each of these images. The target here was to get really high sensitivity, even at the expense of some slight hit to specificity. But really, it's about catching people who might need referral, making sure that they get referred and get treated as needed. And ideally, you get these results live. So once you take the image, you can process it and get the results live. But if you have to wait for a day or a week, that is still consistent with the workflow at most places. So what is the technical piece of this? Well, there's a 5-class rating scale. But for the most part, a lot of the partners we work with really wanted to know just one thing. Do we refer the patient, yes or no? And so in the modeling process, the way we handled this was to say, well, there's a 5-category classification scale here. And the model is outputting 5 numbers, indicating essentially the probability of the input image being in each of these 5 categories. But the final output, the binary yes or no output that we provide, is actually dichotomized, meaning we take the sum of the referable categories, moderate and above, and we check if that is above a certain number. And if it is, we output yes, refer. If it is not, we output no, do not refer. How do we do a data set splitting here? Well, in this case, we had access to partner data, which was what we use for development. We split out a section of it for validation, but in addition, we got another external validation data set over here. But what's interesting in this picture over here is not the validation part, which most of you have a great handle on. You want to check if something's working on data it has not seen before. It is the fact that this development data set here is split up itself. Why is it split up? Well, if we keep checking if we're working out if the model's working well on the final test set, what's going to happen? Well, we'll keep making decisions based on those results. And essentially what will end up happening is that we're essentially training indirectly on this final test set. So what we want to do instead is to be able to make decisions based on some internal tune or validation set over here. And that allows us to keep this entirely held out until we're ready to look at it. We use the convolutional neural network. What that means is it's a form of neural networks that is a little bit more efficient in terms of how the math works out when processing images specifically. The toy example that we saw earlier is not how it looks in reality. This is one example of a, at this point, fairly outdated neural network architecture. But what you see here is repeating patterns of these blocks where there's lots of branches and other things happening. For the most part, you don't need to worry about this. This will get more complicated and longer and larger over time. For the most part, the technical folks will take care of this and try out different things to see empirically what is working on that specific data set. And they do this using the tune data set that we've split out based on the previous slide. In this case, we pre-trained on generic data set, in this case, ImageNet, which is a completely non-medical data set, cats, dogs, buildings, airplanes, cars. And it turns out that helps the model quite a bit. And more generally, why do we do pre-training? Well, we do that because we want the model to be able to extract features as it goes through the layers in a neural network. It speeds up learning, and it reduces the amount of labeled data that you need to develop the final model. Now, what is the model learning? Apologies, this is smaller than I expected. But let's say we were to take the neural network, and lots of people have called this a black box. It's actually not a black box, or at least I beg to differ. And the reason I say that is because we know exactly what each of those million or billion parameters in the network are. We know exactly what it is. This is not a cell where we need to probe it with biochemical experiments, or not tissue where we need electron microscopy and other techniques to look at it. We actually do know what each of those values are. The problem we have is to figure out how do all of these computations fit together to somehow produce the right result each time. Now, for the first layer, we can look directly at the weights. And if we were to plot the weights for a convolutional network, we will start to see usually things like this. And these are little black lines. And what these are edge detectors. Edge detectors means that let's say you have an image where there's a sudden transition from bright to dark. So for example, if it's a fundus photo, you have an optic disc right in the middle that is very, very bright. And the background is, comparatively speaking, darker. When it goes from the transition of the boundary between the disc and the rest of the retina, you're going to see a difference, and it triggers these edge detectors. So the first layer tends to be simple stuff like that, edge detectors. Now, once you get to the second layer, we still know what the weights are, but it's much harder to analyze. And the reason is that the input to the second layer depends on the output of the first layer, which means that it depends on the input that you provide to the network in the first place. So it's really hard to figure out what the second layer is doing, but you can do that for the first layer very easily. Now, people have done other things to look at different layers. One thing they've done is to say, hey, we can isolate each of these neural networks, and we can say what kinds of input will trigger each of these neurons the most. And the way to do that is just by using the math, so the backward pass that I mentioned earlier on. If you were to apply that to specific images, you can then optimize and saturate each of those neurons to make sure that output the maximum possible value. When we do that, we find that the earlier layers tend to be about textures and simpler textures. As you go up the network, those textures become more complicated. And by the time you get to near the top, what you will see are fragments of objects. In this case, this was an ImageNet optimized network, and what we see are things like noses, ears, and other aspects of animals and buildings and aircraft and other things. So you start to see prototype features that it's extracting. And the reason you see a lot of them is because you've asked the neuron to be optimized to produce the maximum possible output. And when you do that, it tries to produce 10 noses as opposed to just one nose. So another challenge that we encountered was how do we handle label noise? Now, this is technical speak for we don't know what the ground truth is sometimes. And what do I mean? Well, here's a plot. Each row here is an image. Each column here is a rater that looked at those images. What we want to see are horizontal bands of colors, sorted from top to bottom. So it should go from blue to green to yellow to orange and then red. What we actually see is that this differs based on the exact image. For the challenging images, for example, this first highlighted row over here, we actually see that it has basically one of every single one of those 5 colors showing up. So that's an instance where the image was probably pretty challenging, so there's ambiguity in what the right label for that image is. How do we handle it? Well, for a start, just at the time of that work, what we did was to just collect more labels per image, and specifically, we collected 800,000 diagnoses for 100,000 images. Now, by doing that, what we could do was to just take the majority vote. What did the majority feel like this image was? And that gives us a very simple but crude way to understand what the right ground truth is for each image. Other things that show up on this slide are things I did not highlight previously, is that in addition to the 5-category grade, that was the primary thing that we were interested in, we were also predicting image quality. And this has implications when you actually deploy a model, because you can then figure out which images are probably a little bit blurry. You should retake it. A little bit too dark. You should figure out dilation or room brightness. And then some sanity checks here in terms of left versus right eye, and which field of view, center versus other areas of the disk. So when we did that, what did we see? Well, this is the way we evaluate performance pretty commonly. If you have not seen one of these before, this is a receiver operating characteristic curve. Very fancy name to say top right is better. And what we saw here was that the model had actually pretty high sensitivity and specificity. And these were these black diamonds here were the threshold that we were using, where we defined the sensitivity and specificity at 2 different cutoffs. And part of the reason we had that was because we wanted to define one which was more sensitive than when we thought most people wanted, or about the same sensitivity, and another one where if you wanted more specificity, you could have an alternative way of cutting the model off. These colored dots here were ophthalmologists that were grading the same images, and so in this case, what you see here is that the black line was similar to where the ophthalmologists were, and recall that this is a zoom in of a very small region of the ROC curve, so the actual difference is even smaller. So is that success? Well, that was good performance, but we wanted to figure out, like, do we actually need to label that many images? 800,000 labels took quite a while, even for us. And so we did 2 experiments. The first experiment was that we reduced the number of labels that we had per image for the training set. So that was the bulk of the data set. When we did that, what we found was this horizontal line over here. For the specific setup that we had, the training data set, as we got more labels, it didn't do very much. Or less labels, it didn't do very much. So going from right to left over here, decreasing number of labels, it was a flat line, basically. However, if we did the same experiment with the tuning dataset, which is the smaller part of the development dataset, once we did that, it started to impact the choices that we're making and therefore the final model performance. Now, caveat over here, this was in a regime where we had 100,000 images to put into the training process. If you're in a different regime with fewer training examples, this might look a little bit different. But the takeaway here is that if you have the option to invest more, then invest more in labeling and getting better quality ground truth for the tuning dataset, because then you can make better decisions about which model is going to be working out better. Now, beyond training and tuning, what else is important? Well, the ground truth is also important when you're doing evaluation, because you need to know what the right answer is. Here's a toy example. In this example, what we have is a model that's predicted 8 items as negative and 2 items as positive, so the blue and the red over here. Now, let's say that we have a ground truth from individual graders, and the ground truth from 3 different graders for the same image looks like this. Between pairs of the raters, say 1 and 2 and 2 and 3, their concordance is about 70%. This is true in this carefully constructed toy example. However, if we were to evaluate the model based on the ground truth from each individual grader, what we see is a spread of accuracies that ranges from 40% to 70 to 100%. That is a massive, massive spread. That is not acceptable, right? This is a toy example. Now, what happens if we got experts who are much more concordant with each other? In this example, the experts are concordant with each other at about 80%, pretty high. And here, when we evaluate the model, we see that its accuracy ranges from 50 to 90%. So a narrower spread compared to before. So that's good. Now, let's say we had panels of experts that came to a consensus on what the right grade for each image is, and that panel has a concordance between each other of 90%, then we get an even narrower spread. So the takeaway here is not to always get panels. The takeaway here is that by measuring the reproducibility of your ground truthing process, it gives you an idea of how stable or unstable the accuracy results that you're getting on your model are. This was very much a toy example, and this is what we highlighted in one of our early articles. More recently, we've had a more theoretical treatment that does something a little bit more complex in terms of sampling and using the fact that we have multiple ratings per rater to compute what we call a uncertainty-aware performance metric, and that gives you essentially builds into the statistical uncertainty, like based on your rater differences. So, from the machine learning perspective, it doesn't care where the label is coming from, right? So the previous examples we saw were from people that were labeling the images, but the label could be from an entirely different modality. So one example over here is where this was for predicting DME. And the example over here, we had the fundus photo as the input to the model, and then the ground truth label coming from OCT. So what this means is that the model is only ever seen a fundus photo, but is tasked with the goal of predicting what the OCT would have shown if you had it. when we did this, what we saw was a change from this purple line over here to this teal or green line over here, where the model actually got much better because the final ground truth was based on this OCT. This is not always possible, but when it is worth trying out. Another interesting thing here is that you could have the label come from something that's not even known at the time of imaging. The example over here is where the input is fundus photo again, and the output, though, are what happens after 2 years. Meaning that this was a retrospective study. We actually had the outcomes of patients, whether they developed DR after 2 years. And then all of the images here, these are individuals who did not have DR at the start of the study. And when we did that, we found that we could actually predict individuals who were going to develop DR in the future. In this line of work, we did additional work here where we worked closely with our partners to do additional prospective and retrospective validation. And in this case, our partners were focused in Thailand and in India. All right, back to this cheat sheet. This has no additional information. I'm going to pause here in case folks want to take photos, but this will conclude the technical modeling part of the work. And I see smartphones coming up, so I'm going to give it a few seconds over here. Great. Moving on, the human-tech interface. Now, the reason this is important is that the real world is not a retrospective study with all of your data in a simple data frame or spreadsheet that looks all nice and tidy. In the real world, there are people lining up, there's workflows, and there's disruption if you introduce any kind of change. So how do you handle that? Well, one way to do it is what we call mixed methods research. And there are experts in this. And what they do is they go talk to the people who are in the workflow and understand every single part of the process and what is happening. The details here are not important, and it's a little bit too small to see anyway, which is good. So don't focus on details. Focus on the fact that each of these boxes are an interaction or a step between an individual, a clinician, for example, and the patient, or between other clinicians. So the important thing here is the fact that there's a lot of steps, even for something like diabetic eye disease screening, where in principle what's happening is that there's a photo being taken and you tell them a result. That's all that's happening. But if you break down every single step that's happening, it's actually a pretty complicated workflow. Now what's important here is that when you have this workflow diagram, you can look at it and interrogate it to see what happens if you introduce a specific change to the workflow. For example, instead of taking a photo and uploading it for graders to take a look at in a week, what happens if you have that same photo being uploaded to the cloud and you get back an answer in 10 seconds? How does the workflow change then? How does scheduling change? Is there internet connectivity in the site that you're working with? What else would actually happen? Do the patient's behavior change because of that? So by understanding all that, it's really, really important for the success of your final ability to implement the AI. Now, by doing this with our partners in Thailand, we did get a prospective study up and running. This involved 9 clinics across Thailand in their national DR screening program and 7,000 participants. Now, the last piece here is a system perspective. Well, what does that mean? Well, the system perspective is hard to understand before you actually deploy or implement the AI. And that takes a lot of work. But what you can do is to simulate it. And in simulations, what people tend to do is to say, well, we know the performance characteristics of the AI. We know how many people we get in the clinic, usually. What will happen if this percentage of them have DR and this percentage are referred? What is the cost to the system to treat the individuals that we do catch, and so forth. Now, as we do that modeling, we see something that's slightly counterintuitive. So look, focusing on the 2 blue bars here on the right, this is a total cost from a provider perspective when you use human graders to do screening versus when you use a model to do screening. A little bit small, but what's important here is that the right plot is higher than the left plot. This is saying that if you use AI, your costs go up. Now, why is that? Well, it's that way because the model is more sensitive than the human graders. So you catch more people with disease, you have to treat more people with disease. And when you do that, the treatment cost starts driving things up. And this blue blocks here is basically all of treatment cost. Now, taking a step back here, why would the system then deploy something that costs them more money? Is that sustainable? Right? So what our collaborators here did was to take a step back. They were part of the national screening program. As they took a step back and looked at what was happening on the system level, what they saw was that if you do not catch disease and people develop blindness, then that has costs on the society. You have to figure out the lost productivity from people who have diabetes, bilateral blindness, and are not able to take care of themselves They are having caretakers and other things. So that has a cost as well. When we factor that in, we actually find that the cost actually favors using AI to do screening. But to do so, you really have to take a step back and look at the overall system perspective. For that specific system, what is happening? All right, so I'm a little bit ahead of time, so I'll spend a bit more time over here. Over here is a slide summarizing some of the lessons we learned, going from developing the code to actually going to the clinic and pushing things out for real-world use. The article here is a viewpoint in Nature Medicine. I'll briefly go over some of the elements. These were covered earlier in the talk as well. On the data front, the quantity is important, but really having the right quality and using the right ground truth, labeling the right data, making sure you know what it is that you're evaluating against and tuning using, that's really key as well. The people that we had, some folks have thought at the start of the journey that really what you wanted are AI experts. They will solve everything. They're the technical people, the 10 people in this room. They will solve everything. But that's not true. You really need a large team that really looks out for a variety of different factors, regulatory aspects, clinicians, statisticians, user interface, and more. It was really a huge team endeavor that brought us here. Now, readiness to launch. Traditionally, we have thought, well, we have a performance target over here. Once we hit it, where we go? We should just go live. Turns out it's more complicated. We do want repeated validations in many different settings, a diversity of data that you're evaluating on. You really need to be pretty sure that you're doing well before you go out there in the real world using our real patients in real workflows. In our trial, the way we handle some of this stuff is that we had a safety element built in there where when a patient shows up for the clinic in that Thailand trial, the screening decisions were made using the AI. It was a prospective interventional trial. But what was actually happening in the background was that that same image went to a grader, and if the grader then disagreed with what the AI was outputting, the clinic was informed so they can call the patients back for a screening if that was needed. So we did this as a safety measure. Integration and workflow. This is what we covered in terms of understanding workflow, what changes when we introduce something different. Sometimes it's something as simple as providing a hotspot so they have internet access. Other times it's moving a computer from room A to room B because that was where the internet access was. Other times you might need to change the workflow more dramatically to make this work out. And the last thing, we did not cover this, but it's about after you launch this, what happens? Well, in this case, because this was a cloud-based AI API, we could monitor the predictions and continue to keep track of what's going on. So if there were some performance changes, we can investigate it and figure out if any changes were needed. With that, I conclude most of my talk. I'll highlight again the three main takeaways. There's the technical modeling piece, but that's not it. That's not all that there is. There's the human tech interface, and then there's the systems perspective. If you want a snapshot of those main lessons, that's this slide right over here, waiting for the cameras again. And very pleased to share that as of now, there's been over 250,000 people that were screened using AI we have developed, and very privileged to work with our partners on this. And I will pause there to take any questions.
Thank you so much, Yoon.